Every day, countless satellites orbit our planet, playing vital roles in our daily lives. It's fascinating to think that nearly 4,900 satellites are currently circling the Earth. This raises some interesting questions. Why do these satellites occupy different orbits? How do they perform their functions? And what components do they contain that enable them to carry out their tasks? Let's delve into these questions in more detail. A satellite remains in orbit due to a delicate balance between gravitational pull and centrifugal force. The angular velocity of a satellite is determined by a force balance equation that stabilizes these opposing forces. When a satellite is launched, it is given enough speed to maintain this balance. Satellites closer to Earth must travel at higher speeds to counteract stronger gravitational forces compared to those farther away. Because there is virtually no resistance in space, satellites maintain their speed indefinitely, allowing them to orbit the Earth continuously without needing an external power source. Satellites are positioned in various orbits, including low Earth orbit, LEO, medium Earth orbit, MEO, and geosynchronous Earth orbit, GEO. Each orbit serves different purposes, which we will explore shortly. An intriguing region in space known as the Van Allen belt contains highly energetic charged particles that can severely damage a satellite's electronics. For this reason, satellites are typically not placed within this belt. The choice of orbit depends on the satellite's intended application and purpose. For instance, satellites designed for Earth observation, weather forecasting, geographical surveys, or satellite phone communication are often placed in orbits closer to Earth. LEO, ranging from 160 to 2,000 kilometers above Earth, has an orbital period of approximately 1.5 hours. However, LEO satellites cover smaller areas, so multiple satellites are required for global coverage. This is why high orbits like GEO are preferred for tasks such as broadcasting. Satellites in geosynchronous orbit, located at an altitude of 35,786 kilometers, rotate at the same speed as the Earth, taking exactly 23 hours, 56 minutes, and 4 seconds to complete one orbit. Within this category, geostationary satellites are aligned with the Earth's equator, remaining stationary relative to the Earth's surface. This makes them ideal for television broadcasting, as it eliminates the need to constantly adjust satellite dishes. The geostationary belt, densely populated with satellites, is managed by the International Telecommunication Union, ITU. Geosynchronous orbits are also home to some navigation satellites. GEO satellites can cover up to 1/3 of the Earth's surface, meaning only 3 satellites are needed for global coverage. For navigation systems like GPS, MEO is often the optimal choice. Although LEO satellites are closer to Earth, their high speed can hinder accurate navigation calculations. Additionally, LEO requires more satellites to achieve complete Earth coverage, making MEO a more efficient option for GPS. Typically, 24 satellites in MEO are sufficient to cover the entire globe, with an orbital period of about 12 hours. Let's now examine the primary components of a communications satellite and their functions. At the core of these satellites are transponders, which handle tasks such as frequency conversion, noise reduction, and signal amplification. For instance, on Ku-band satellites, transponders convert signals from 14 GHz to 12 GHz, with each satellite potentially housing 20 or more transponders. These transponders require significant electrical power to operate. Satellites are equipped with solar panels and batteries to meet their power needs. Solar panels power the satellite's electronics, while batteries are used during eclipses. A sun sensor on the satellite helps orient the solar panels to maximize energy capture from the sun. The input signal is typically received by reflector antennas, the most common type of antenna on satellites. Satellites are expected to maintain their designated orbits. However, The gravitational field around the satellite is uneven due to Earth's irregular mass distribution and the gravitational influence of the Moon and Sun. This can cause the satellite to drift from its intended position, which is a risky situation as it could lead to a loss of signal. To correct this, satellites use thrusters to reposition themselves. These thrusters also help avoid space debris. The necessary fuel for the thrusters is stored in tanks within the satellite. The satellite's position, health, and speed are continuously monitored by Earth stations using tracking, telemetry, and control systems. These systems maintain communication between the satellite and Earth by transmitting signals at different frequencies to avoid interference with other communication signals. What happens when a satellite becomes non-operational, or its lifespan is ending? These inactive satellites can pose a threat to other functioning satellites or spacecraft. To mitigate this risk, non-functional satellites are moved to a graveyard orbit by activating their thrusters. By increasing the satellite's rotational speed, it can be moved to a higher orbit. The graveyard orbit is located several hundred kilometers above the geostationary orbit. This maneuver consumes as much fuel as a satellite would need for about 3 months of regular station keeping. Communication satellites, GPS satellites, and Earth observation satellites each have specific components tailored to their missions. For example, GPS satellites rely heavily on atomic clocks and L-band navigation antennas. Earth observation satellites, typically in LEO, are equipped with various sensors and imagers suited to their specific tasks. You might have noticed that satellites in this video are covered with a gold-colored material. Contrary to appearances, this is not simply foil but a multi-layered structure designed to protect the satellite from the extreme temperature variations and intense solar radiation in space. Temperatures in space can range from -150 to 200 degrees Celsius, and this protective material acts as a shield to maintain the satellite's functionality.